Hello, welcome to the first tutorial video on complex numbers. I am Mexams, and in this video I will take you through the introduction to complex numbers and complex numbers algebra. If you are new to my channel and this is the first time you are watching a video on my channel, kindly subscribe to the channel for more video. Okay, so let's start. Complex numbers. Okay, so what brought about complex numbers? Okay, so let's take into consideration this quadratic equation. Okay, so if you have a quadratic equation, say s squared plus 1 is equal to 0. This is a quadratic equation. Okay, so we are supposed to find and solve for the roots of this quadratic equation. Okay, how do I compute the roots? Okay, for a normal equation, this is what we would have done. We would have done s squared is equal to what? -1. And so this will generate what? X equals the square root of what? -1. Now, on a normal real line, there's no solution for such situation. Okay, so mathematicians came to a conclusion that let's give some imaginary representation of square root of negative numbers. Okay, so they said that let's square root of what? -1 be equal to I. Okay, so if square root of -1 is equal to I, then it means we are doing what we call them complex numbers. So in complex numbers, actually we are trying to represent square root of negative numbers with some symbols. Okay, all right, so if this is the case, then it means what if we have square root of -2? How do you compute this? Okay, so from simple said simplifications, okay, this can be rewritten as what? Square root of -1 times 2. Okay, and this is equal to square root of -1 times square root of 2. So but we say square root of -1 is what? I. So this becomes square root of 2 times I. Okay, I hope this is okay. This is very simple, right? So let's take other examples and simplify them, and you know. Okay, so the basic thing here is that you are supposed to put in mind that always I represents square root of what? -1. Okay, what if I have square root of -4? Okay, something like this. This is equal to, from the said definition that I did, square root of -1 times 4. So instead, this is also equal to square root of -1 times square root of 4. And square root of 4 is what? 2. And square root of -1, we are saying in complex numbers, is what? I. So it becomes 2i. Okay, so whenever you see something like 2i, 3i, means it was a square root of some negative number. Okay, I hope this is okay. So from this definition, what are some of the numbers that we call complex numbers? Okay, so let's look at some examples of complex numbers. All right, some examples of complex numbers. Okay, so if I write a complex number, say z, we normally represent complex numbers by z. Okay, so if I write z equals, normally all complex numbers are being represented in two parts. First part is the real part, and the other part is the imaginary part of pardon me, my handwriting is somehow not nice. Okay, so that is it. So if I have this as my complex number, the first part, like I said, this part is what we call the real part. Okay, this is the real part, and this part is the imaginary part. Okay, imaginary. Okay, so with this, I hope you can write any complex number. Okay, so if I write a complex number, say like we said, complex numbers are being represented as what? Z. So if I write z being equal to, let's say, 2 plus 3i, then it means 2 here is what? 2 is what? The real part, and 3 is what? The imaginary part. Okay, I hope you get it right. So these are what we call complex numbers. So any complex numbers can be represented as this. But there are some cases, some special cases, special occasions that some complex numbers comes with either the real part alone or the imaginary part alone. So if a complex number, say z is equal to, let's say, a, this will only happen whenever b is what? 0. When b is 0, we have the complex number z will be what? How do you call it? It will be just the real part will only be available for us. Okay, so complex numbers like this is called what you called purely real complex number. Okay, so if a complex number is purely real, then it means that the imaginary aspect is what? 0. What if the real part is 0, and then you have something like this? Then this is also called purely imaginary. Okay, so with this notation, with this side, the purely real, the side, this means that every real number is a purely real complex number. I hope that is okay. I hope you can see, because every real number is being represented as something like let me erase some parts and write them. So if you have every real number, like we know from the real number system, every real number can be written as, say, let's say 2. So if I have 2, it means that this 2 as a number is a complex number where the imaginary part is what? 0. I hope you get it. Okay, so let's look at some cases, some special cases for complex numbers. Okay, let me erase this one. Okay, so we have some parts, some properties of complex numbers that are special. Okay, we have what we call the conjugate of a complex number, and also the argument of a complex, that is the modulus or the length of a complex number. We talk about all of them, but let's talk about the conjugate of a complex number. Okay, so if I have conjugates, okay, so the conjugate of a complex number, if I have a complex number z equals this side, then the conjugate complex number of z, which is called the z bar, is equal to a minus bi. Okay, so with the a minus bi, you could see that everything with this and the original complex number, they have the same properties, they have the same thing, but the only problem is that the sign between the two of them, that is between the imaginary and the real, is negative. It's different. Okay, it's the opposite of each other. So if I have complex number, say w being equal to c plus di, then its conjugate w bar will be c minus what? Di. Okay, they're very simple, right? So if I have a purely real complex number, something like z equals a, like we did first, okay, something like this, then its conjugate z, we are supposed to what? Negate the sign that is in front the real part, the imaginary part. Okay, like we said first, we said that for purely real complex numbers, the imaginary aspect is what? 0. So like this. Okay, so it means that the z bar will be what? Equal to a minus 0i, and this will still give me a. So it means that if I have a complex number that is purely real, then its conjugate, that is a complex conjugate z bar, z equals a, then z bar will also be equal to what? A. The same thing. Nothing changes here. I hope this is okay, right? Okay. Let's look at the case where the real part is rather 0, and so that because of that we will have what? Purely imaginary, right? So if the real part is 0, then it means we have our complex number being what? Let's say bi or ib. Some books use ib. Let me erase this one. Some books uses ib, so you can write ib or bi, meaning the components of what the real component of the complex number is that. Okay, then it means that my complex number is actually written as 0 plus bi. Then this will implies that my z bar, that is the complex conjugate of this complex number, is actually equal to 0 minus bi, and 0 minus bi will give me what? Z bar being equal to what? Negative bi. Okay, so if the complex number is purely imaginary, then its conjugate is also negative of the imaginary part. Okay, I hope this is okay. All right, so let's move on and look at some algebraic computation of some complex numbers, so addition and subtraction of complex numbers. How do you add and subtract complex numbers? Okay, so if I have a complex number, say z1 being as a plus bi, and z2 giving us c plus di, then z1 you are doing the addition first, plus z2 is equal to, you just add the real parts, then you add the imaginary parts. Okay, so you pick the real part a, then this one, the real part for z1 is what? A, and the real part for z2 is what? C. So it becomes a plus c. Okay, then you put that in a bracket, you add them separately, then plus you add the imaginary aspects b plus d. Since they are all being attached with I, you just write I like that. So in simple terms, it's like you are factorizing the I out. Okay, so it becomes b plus d, then all I. Let's give a real example and then you understand. So let's say we are giving z1 being equal to, let's say, 2 minus I. Okay, and z2 being equal to, let's say, 3 plus 2i. Then I write z1 plus z2. Then this will be equal to, we are saying that you should add the real part. Okay, so it becomes 2, this 2 becomes this 2, then you add it to this 3. Okay, and this will produce what? 5. It becomes 2 plus, let me write it here so that you see it clearly. Okay, becomes 2 plus 3, then plus, you're saying that you add the imaginary components as well. So here we have negative 1 I. It's like negative 1 I. There's a 2 I here, so we can negative 1 plus 2, then I, and this will give us a product, a resulting solution of 5 plus I. This is pretty simple, right? Very simple like that. Okay, so that is how you add any other complex number. Let's look at something. Let's erase this. Let's look at something about complex numbers, addition of complex numbers and their conjugate complex numbers. Okay, so as you already know about the conjugate of a complex number, let's try to bring that idea here and see, whenever you do z1 bar, that is what its conjugate is, what? A minus bi. That is what we said. Now I want to add a1 z1 and its conjugate, right? I want to add them. Then this means that z1 plus z1 bar is actually equal to a plus bi plus a minus bi. You are saying that you add this like that, and then in so doing you just add what? The components, the real to real. So 1a plus a becomes what? 2a. Then bi minus, that is plus, minus bi, that will become what? 0i. So in other words, whenever you add a complex number and its conjugate, let me write it well. Whenever you add a complex number and its conjugate, you always produce a real number. Okay. Whenever, I like writing this first. Okay. You always produce a real number. That is a purely real complex number. Okay. That is it. That is it for this. Okay. What if I want to subtract a complex number and its conjugate? What happens? Okay. If you want to subtract, what happens? Let's look at the subtraction as well. So if I want to subtract a complex number and its conjugate, then the effect will be on the real part. This is the case. Z1 minus its conjugate. Okay, that's Z1 bar is equal to a plus bi, then minus in brackets a minus bi. I hope this is okay. So this z1 minus z1 bar is equal to, all right, a plus bi minus a plus, because negative will go into this and become plus bi again. Now z1 minus z1 bar is equal to a minus a becomes 0, so bi plus bi, I get what? 2bi. So whenever you subtract a complex number and its conjugate, you always produce a purely imaginary complex number. Now these are not what you are interested in. You are interested in writing a complex number, okay, the terms, that is the imaginary part and the real part, in terms of its conjugate and the main complex number. Okay, let's try to deduce that and see. There is a special formula that we are going to deduce from what we've already known. Okay, I hope you've written them down, because I'm just going to write them. We are saying that z1 plus z1 bar is always equal to 2a. That is just 2 times the real part. Okay, we are saying that z1 minus z1 bar, okay, z1 minus z1 bar, we are saying that this is equal to 2bi, right? Now from these equations, let's say equation 1 and equation 2. So from equation 1, I can make a the subject. Okay, so always the real part of a complex number is equal to, if I divide the whole of this equation 1 by 2, I'll get z1 plus z1 bar over 2. So always our real part of our complex number is given as this. Then we come to the equation 2 to find our b. Now if I want to divide through by 2i, then our b will also be equal to z1 minus z1 bar all over 2i. Okay, so keep these equations in mind. Okay, keep them in mind, because there might be questions that you'll be given the complex conjugates and other stuff, then you'll be asked to find your a and b, the actual complex number. Okay, we can give you a question where you omit some of these and we ask you to find the actual complex number. Okay, so that is it. Let's try to continue with what we are doing here. You could see that at the at this side, the numerator here, okay, the denominator here, there is a 2I at the denominator. Okay, you should know that in doing division of complex numbers, that is different. The way we do it is like doing said division. Okay, so when you get to that part, I will explain and then you understand. So let's look at multiplication of complex numbers. Okay, here we have a very interesting subtopic that we will talk about here. All right, we know that the multiplication of anything, we just multiply the thing and then you go, right? So let's look at this. We said in our first statement that I is equal to what? Square root of -1. Okay, so we keep them always, this is in our mind. Okay, now let's try to do some multiplication of I by itself and know the powers of I. Now from indices, if I have I squared, it means I times itself, so it becomes what? I times I, right? And this is equal to what? This will give me what? Square root of -1 times square root of what? -1. And this will give me what? Square root of -1 all squared, and that will give me -1. So immediately we've known that I squared is always what? -1. Keep it in mind. Alright, so let's look at I cube. This will give me I times I times I from indices, and this is equal to square root of -1 times square root of -1 times another square root of -1, and this is equal to what? Look, square root of this side times this side will give us what? -1, then times another square root of -1. Now you know that square root of -1, we can't do anything about it. You just have to represent it by what? Our I here. Okay, you know that square root of -1 is what? I, and this, there's a -1 multiplying it, so it becomes what? Negative what? I. So put this in mind also, that always the I to the power 3 is what? -I. So keep these, the ones I'm circling, I'm putting a circle on. Okay, let's look at I to the power 4. Okay, let's look at this. I raised to the power 4. This is equal to what? I times I times another I times another I, and this will give me what? Square root of -1 times square root of -1 times square root of -1 times another square root of what? -1. This, they are 4, right? So this is equal to, this times this will give me what? -1 times, then the last two, this also times this is also what? -1. Now negative times negative is what? Positive, so it gives us +1. Okay, also put this in mind, okay, that I to the power 4 is also what? 1. So if let's say you've been given some simplifications to do, that you have I squared to do, you know that I squared is also always equal to what? -1. You know that I to the power 3 is always equal to -I, and I to the power 4 is also what? 1. Now this will take us to a general solution, a generalized way of finding every power of I. Okay, so let's clean this and write them properly and you understand. Okay, we want to write a formula that whatever power of I that we will be given, we get it right, and then we just use the formula and then everything will be okay. Okay, now the reason why I stopped under I to the power 4 is because if you continue to I to the power 5, let's do that, and you will see I to the power 5, it will simply be I to the power 1, okay, then times I to the power 4, right, from indices. And now I to the power 4 is what? 1. And so I times 1 will be what? I. Now I to the power 6 will also be equal to what? I squared times I to the power 4. And I to the power 4 we know is always 1. So it becomes I squared is also what? -1. So it becomes -1 times 1, which is equal to -1. Alright, so I just wanted to show you something why I've stopped. So this means that we can generate all the powers of i's using just I to the power 4, I to the power 3, and I to the power 2. Okay, so let's look at this general thing. Powers of I. This implies that we are saying that I is equal to a square root of -1. Just put this in mind. And I squared is what? -1. I cube is equal to what? -I, and I to the power 4 is equal to 1. So let's put this in mind. We are going to deduce something. Now, from indices, if I have I to the power m, okay, if I have I to the power m, and I can rewrite this whole I to the power m, I can rewrite this as something, okay, in terms of multiplication of multiples of 4. Sorry, the m in terms of multiples of 4. Okay, so actually it's not the whole of this that I'm trying to write in terms of 4. I'm trying to write m. What is this? You want to solve this. Okay, so if I can write m as, let's say, 4 times a certain n plus a certain constant, let's say c, where c is less than 4, okay, such that c is less than 4, okay, this condition should be satisfied. Then it means that c will actually be equal to, either 0, 1, 2, or 3, because this is just counting, and this is a natural number. The power should be a natural number. Okay, actually that is this m should belong to the natural numbers, okay, before this works. All right, if that is the case, then it means I to the power n that I've written here can be rewritten as what? I to the power what? 4n plus c. And this whole thing can be rewritten as what? I to the power 4n dot or times I to the power c. From indices, this is true, right? But from indices, the same I to the power 4n. Let's check something. Can be written as I to the power 4 or to the power n, where I to the power 4 that we know is what? 1. So it becomes 1 to the power n, and that will give me 1. So actually the whole of this will give me what? I to the power what? C, where our c belongs to either one of these. Okay, so let me clean everything so that we write it properly. Okay, that this I hope you can see, right? You understand everything. Okay, if you don't understand anything, just go to the comment section and comment, and I will come and explain it back in our next video. Okay, so let's talk about it again. Let's write our general formula properly, and after that everything will be okay for us. Okay, now we are saying that if I have I to the power m, some powers of I, okay, some I to the power m, and I can rewrite m as we did, like we did, sorry, the I, there should be a 4n plus some c, where c belongs to either 0, 1, or 2, or 3, right? Then this should be equal to I to the power c. Okay, if I can rewrite this as that, where our c is always either one of these, 0, 1, 2, 3. Now let's take a practical example and see. Simplify I to the power 100. Okay, how do I simplify I to the power 100? Now I to the power 100, I know 100 can be written as what? 100, 100 can be written as what? 4 times 25. Okay, so if you want, you can divide the 100 by 4 and see if you can write that. So this implies that we know that 100 is equal to 4 times 25, okay, plus 0, because the remainder 4 times 25 is 100. Okay, so it means that I to the power 100 here is equal to I to the power what? 4 times 25 plus C. Okay, now we are seeing from this general equation, from this general equation here, from the equation here, we are saying that okay, so from the general equation we are saying that this whole thing, if we can have some C, then the whole of this equation can be written as I to the power C here. Okay, if that is true, then you come here and check our C for this. This is 25, please. Let me erase it and write it properly. $25. Okay, so our C here is what? 0. So we just write our 0 there, and so this becomes I to the power what? 0. And from indices, any number to the power 0 is what? 1. So if you go and see a bigger value, like simplify I to the power 1200. Okay, I hope you can do this. 1200. All right, this one I won't do, and I'll expect you to do it, okay, by yourself. I to the power 200, sorry, 1200. Okay, so that is it for the powers of i's. Okay, now let's look at the real multiplication of complex numbers. Okay, how do you multiply two complex numbers where you don't have just a single I, but you have a complex number given in terms of A and B? Okay, how do you know, or how do you do the multiplication? All right, so let's see. If I have a complex number, say Z, like we started with, being equal to A plus BI, okay, and let's say W being equal to C plus DI, then Z times W, just this is very simple, right? This is very, very simple, because the multiplication of this is simply just multiplying like we know in normal algebra. Okay, just A plus BI, you write it, then times C plus DI. So now in doing this multiplication, you just expand the brackets from the way of doing normal algebra expansion. Okay, so A times C will give me AC, then plus A times DI will give me what? ADI, then plus BI times C becomes CBI, then plus BI times DI becomes BD, then I squared. Okay, that's why we did the powers of I. Okay, and this will give me what? Look at this, AC, okay, plus AD plus CB or BC. I'm sorry. Okay, so it's AD. The reason why I'm just doing this is because I have ADI here, I have BC or CBI here. From this I can add them, because you said in complex numbers addition you just add the I components, okay, and then you add the real components. So it becomes AD into bracket plus CB or BC, anyhow you want to write it. Multiplication is commutative, okay. Then I, then here I squared is what? From the previous ones that we did, I squared is -1, so it will become -1 times BD. It becomes minus BD, okay. Now we have the real part AC. There is no I attached to this. There is no I attached to this BD. There's no I attached to this AC, so it becomes AC minus BD, then plus AD plus CB or I, okay. So this is very simple, right? This is very simple to go by. So let's take a normal example, one example, and solve, and then after that you'll be okay. All right, I hope you understand. Okay, let me write it again in case you didn't get it. So we said it's AD plus CB, then I, right? Okay, this is C. Okay, so let me erase it from the top. And so if you didn't get it well, you can copy and put it somewhere, and always do revision on it. Okay, so what if we are given a real life problem, real life complex numbers to compute for? Okay, let's look at it very quick and it will be fine. Okay, so like I said, if I have z equals, let's say 2 plus I, then w equals, let's say 3 minus 2I. Let me use this. Okay, then if I want to do multiplication, it says simply z times w will be equal to what? 2 plus I times 3 minus 2I, and this is just 2 times 3, just expansion, normal expansion, becomes 6. Then 2 times -2I become minus 4I. Then I times 3 becomes what? 3I. And I times -2I, so it becomes -2 times I squared, which is -1. Okay, and this will give us what? 6 minus, or let's say plus, in bracket, -4 plus 3, then I, then plus 2. So this becomes what? 8 minus I, because you are adding this side 6 and this 2. They are just real, so you add them, and you add this and this, you get -I. So that is it. Very simple, right? Okay, so there is this shortcut that you can also use. Okay, there's a shortcut that I want to teach, so that in case you are not given numbers and some expression, you want to find a multiplication fast and go. Okay, within just 30 seconds you'll be able to solve. I said earlier, we found out earlier that, let's use a different color. Let's try to use a different color for the shortcut. So that if you have z equals a plus bi, then w equals c plus di. Okay, now you are just multiplying them, z times w. You are saying this will be equal to, first you take the first one here, you multiply it by this one, that is AC. Okay, then it will be minus, you take this one and you multiply this by that. Okay, it become BD. Sorry, let me erase it. So this will become BD. Okay, then you take the first one again, you multiply it to the last one. So this time you use plus, so it's plus minus plus again. Okay, so it becomes AD. Then plus, this time around it becomes plus B times C. So it's like the first one times the first one, last times last, then you subtract them. Then this one comes first times last, last times first. Okay, so B times C become BC. I. So if you can remember this like that would be pretty fine. But if you don't remember it, you can still go through um, formula or a worked example and then solve it like how you understand it. Okay. So let's clean it and do another one. Okay, so let's try to do the division of complex numbers. How do you divide complex numbers? Okay. How do you divide complex numbers? So if I want to divide a complex number, sorry, if I want to divide two complex numbers, which one should I pick? Okay. So if I want to divide a complex number, okay, let's say I have this complex number. Let's say I have, sorry. Let's say I have a complex number, say z equals, let's say a plus bi and w equals c plus di. Okay. With this, and I want to find the division, that is either z divided by w or w divided by z. So I have z over w. If I want to do this, okay, if I want to do this, then how do I find the division? Okay, this is equal to a plus bi over c plus di, right? Now with this, what you do is you first find the conjugate of the denominator. Okay, now the conjugate of w is what, w bar, and that is equal to c minus di. Okay, you've done it already. Then after that, you multiply by both numerator and denominator. Okay, so this is how it goes: c minus di over c minus di. Okay, so then you do your normal multiplication of fractions. Okay, I hope you can do normal multiplication of fractions. So z over w will actually be equal to the top multiplying by the top, so it becomes a plus bi times c minus di. Then this becomes c plus di, c minus di. Then you do your normal multiplication. Okay, let me reduce the size because I think the size is too big. Okay, so with this is equal to you know the top will always be the same. Okay, I'm coming. Let's erase some parts. I hope you got this part. So let's erase this part and simplify the expression down here to the simplest form. So like we said, z over w, this is equal to, all right, the top, you know how to do multiplication. So the first one times the first one, so it becomes ac, then minus the last one times the last one. Okay, so it becomes minus b times d, and it becomes plus. Okay, because b times negative d, sorry, so it becomes plus, it becomes bd. Alright, then plus first one times last one, that is ad, plus this one is here you add, sorry, this is minus ad, minus ad because the d is negative here, so minus ad plus then b times c, so bc I. Then this whole thing over, look at this. If you could see, there's a c here, there's a c here, there's a plus di here, there's a minus di. What do you see? This is what difference of two squares. Okay, so simply this becomes c squared minus what? di all squared. And the whole of this denominator will give us what? C squared, then minus d squared I squared, and d squared I squared will give us a negative one, so we can minus d squared. That would be what? Plus d squared. So in other words, we can rewrite the whole of this denominator as what? C squared plus d squared. Okay, that is it for it. Okay, in fact, we're supposed to do multiplication of a complex number and its conjugate complex number, but then I hope we're able to understand this. Okay, so let's keep the formula in mind, and then this formula, let's keep this formula in mind, and then let's try to do some simple example, and then we'll understand. Okay, so like I was saying, if you have a complex number and it conjugates and you want to do the multiplication, it's simply the real parts squared plus the imaginary part squared. That is all. Okay, that is all for the complex number. We have something that we call the modulus of the complex number. We'll get to there when we do video on that. We actually talk about the relationship between the complex number and its conjugate, and then the modulus of it. Okay, so let's take time to quickly go through this. Okay, if I have a complex number a plus bi and its conjugate being a minus bi, then z times z bar, like I said, is what? A plus bi times a minus bi, and this is what? Difference of two squares, so this becomes a squared minus what? Bi all squared, and so this will give us a squared minus b squared I squared from indices. This will produce what? A squared minus b squared into -1. Now the -1 will affect the b squared, so we count a squared plus b squared. So like I said, if you have a complex number and you're multiplying it by a conjugate, then it's simply the real part squared plus the imaginary part squared. Okay, I hope you understand it. Okay, let's take an example on the division, and then after that you will really understand the division of complex numbers. Okay, let's take a very simple one, very simple one, and that will be okay. I hope you understand. If you don't understand, like I said, you can also comment, and then when I say it, I will explain it to you in our next video. Okay, please, if this is your first time, like I said, of watching a video on my channel, just try to subscribe, and then you get notified anytime I upload a new video. Okay, so let's take this example. If I have the complex number, say z equals 1 plus I, and w equals 2 plus I. Let's take this. Okay, then z over w is actually equal to 1 plus I over 2 plus what? I, and this is equal to 1 plus I times, we are saying both numerator and denominator by the conjugate of what? The denominator, 2 minus I. Okay, all over 2 plus I, 2 minus I. Okay, and this will give us 1 times 2 becomes 2, 1 times this becomes -I plus 2I, then -I times I, so we can negative times I squared. I squared is -1, and times negative becomes what? So it's -I times I. Okay, this whole of this over, like we said, this side, if you simplify, you get something like the real power squared plus the imaginary power squared. Okay, and this will give us 2. Then look at this side, negative I times I, so it's I times I, which will be I squared times -1, and that will be I squared is what, -1 times this negative that is in front of this, and that will give us positive, so become 2 plus 1, that the whole of this will give us +1, then plus I all over 5. Okay, sorry, 16 plus 1, that will be what, 17. I saw it before, so I'm sorry for that. It's the whole of this over what, 17, and this is equal to 3 plus I over 17. Okay, so in other books they will try to simplify it to the lowest and be like 3 over 17 plus I over 17, or you can say 3 over 17 plus 1 over 17 I. Mostly this is how they write it. Okay, alright, so that is it for this tutorial. Thank you and see you next time. Please subscribe to my channel for more videos like I said.